is a combination of processes that are used to prepare semiconducting materials for ICs. One process is called thermal oxidation, which forms silicon dioxide on the surface of the silicon. This is used as a gate insulator and field oxide. Other processes are called photomasks and photolithography. This process is what creates the patterns on the circuit in the integrated circuit. Ultraviolet light is used along with a photoresist layer to create a chemical change that generates the patterns for the circuit. 4. The etching is the next process that is required. The part of the silicon that was not covered by the photoresist layer from the previous step can now be etched. The main process typically used today is called plasma etching. Plasma etching usually involves an etch gas pumped in a low-pressure chamber to create a plasma. A common etch gas is chlorofluorocarbon, or more commonly known freon. A high radio frequency voltage between the cathode and anode is what creates the plasma in the chamber. The silicon wafer is located on the cathode, which causes it to be hit by the positively charged ions that are released from the plasma. The result is silicon that is etched anisotropically. 4. The last process is called diffusion. This is the process that gives the semiconducting material its desired semiconducting properties. It is also known as doping. The process introduces an impure atom to the system, which creates the p-n junction. To get the impure atoms embedded in the silicon wafer, the wafer is first put in a 1100 degrees Celsius chamber. The atoms are injected in and eventually diffuse with the silicon. After the process is completed and the silicon has reached room temperature, the doping process is done and the semiconducting material is ready to be used in an integrated circuit. 4. Physics of semiconductors. Energy bands and electrical conduction. Filling of the electronic states in various types of materials at equilibrium. Here, height is energy while width is the density of available states for a certain energy in the material listed. The shade follows the Fermi-Dirac distribution, black, all states filled, white, no state filled. In metals and semimetals the Fermi level F lies inside at least one band. In insulators and semiconductors the Fermi level is inside a bandgap. However, in semiconductors the bands are near enough to the Fermi level to be thermally populated with electrons or holes. Semiconductors are defined by the unique electric conductive behavior somewhere between that of a conductor and an insulator. 10. The differences between these materials can be understood in terms of the quantum states for electrons, each of which may contain 0 or 1 electron, by the Pauli exclusion principle. These states are associated with the electronic band structure of material. Electrical conductivity rises due to the presence of electrons in states that are delocalized, extending through the material. However, in order to transport electrons a state must be partially filled, containing an electron only part of the time. 11. If the state is always occupied with an electron, then it is inert, blocking the passage of other electrons via that state. The energies of these quantum states are critical since a state is partially filled only if its energy is near the Fermi level. See Fermi-Dirac statistics. High conductivity in material comes from it having many partially filled states and much state delocalization. Metals are good electrical conductors and have many partially filled states with energies near the Fermi level. Insulators, by contrast, have few partially filled states. Their Fermi levels sit within bandgaps with few energy states to occupy. Importantly, an insulator can be made to conduct by increasing its temperature. Heating provides energy to promote some electrons across the bandgap, inducing partially filled states in both the band of states beneath the band gap, valence band, and the band of states above the bandgap, conduction band. An intrinsic Semiconductor has a bandgap that is smaller than that of an insulator, and at room temperature, significant numbers of electrons can be excited to cross the band gap. 12. A pure semiconductor, however, is not very useful, as it is neither a very good insulator nor a very good conductor. However, one important feature of semiconductors, and some insulators, known as semi-insulators, is that their conductivity can be increased and controlled by doping with impurities and gating with electric fields. Doping and gating move either the conduction or valence band much closer to the Fermi level and greatly increase the number of partially filled states. Some wider bandgap semiconductor materials are sometimes referred to as semi-insulators. When undoped, these have electrical conductivity nearer to that of electrical insulators, however they can be doped, making them as useful as semiconductors. Semi-insulators find niche applications in microelectronics, such as substrates for HEMT. An example of a common semi-insulator is gallium arsenide. 13. Some materials, such as titanium dioxide, can even be used as insulating materials for some applications while being treated as wide-gap semiconductors for other applications. Charge carriers, electrons and holes. The partial filling of the states at the bottom of the conduction band can be understood as adding electrons to that band. The electrons do not stay indefinitely, due to the natural thermal recombination, but they can move around for some time. The actual concentration of electrons is typically very dilute, and so, unlike in metals, it is possible to think of the electrons in the conduction band of a semiconductor as a sort of classical ideal gas, where the electrons fly around freely without being subject to the Pauli exclusion principle. In most semiconductors, the conduction bands have a parabolic dispersion relation, and so these electrons respond to forces, electric field, magnetic field, etc., much as they would in a vacuum, thou with a different effective mass. 12. Because the electrons behave like an ideal gas, one may also think about conduction in very simplistic terms such as the Drude model, and introduce concepts such as electron mobility. For partial filling at the top of the valence band, it is helpful to introduce the concept of an electron hole. Although the electrons in the valence band are always moving around, a completely full valence band is inert, not conducting any current. If an electron is taken out of the valence band, then the trajectory that the electron would normally have taken is now missing its charge. For the purposes of electric current, this combination of the full valence band, minus the electron, can be converted into a picture of a completely empty band containing a positively charged particle that moves in the same way as the electron. Combine it with the negative effective mass of the electrons at the top of the valence band, we arrive at a picture of a positively charged particle that responds to electric and magnetic fields just as a normal positively charged particle would do in a vacuum, again with some positive effective mass. 12. This particle is called a hole, and the collection of holes in the valence band can again be understood in simple classical terms, as with electrons in the conduction band. Carrier generation and recombination. When ionizing radiation strikes a semiconductor, it may excite an electron out of its energy level and consequently leave a hole. This process is known as electron-hole pair generation. Electron-hole pairs are constantly generated from thermal energy as well, in the absence of any external energy source. Electron-hole pairs are also apt to recombine. Conservation of energy demands that these recombination events, in which an electron loses an amount of energy larger than the band gap, be accompanied by the emission of thermal energy, in the form of phonons, or radiation, in the form of photons. In some states, the generation and recombination of electron-hole pairs are in equipoise. The number of electron-hole pairs in the steady state at a given temperature is determined by quantum statistical mechanics. The precise quantum mechanical mechanisms of generation and recombination are governed by the conservation of energy and conservation of momentum. As the probability that electrons and holes meet together is proportional to the product of their numbers, the product is in the steady state nearly constant at a given temperature, providing that there is no significant electric field, which might flush carriers of both types, or move them from neighbor regions containing more of them to meet together, or externally driven pair generation. The product is a function of the temperature, as the probability of getting enough thermal energy to produce a pair increases with temperature, being approximately exp, e.g/kt, where K is Boltzmann's constant, T is the absolute temperature and Eg is band gap. The probability of meeting is increased by carrier traps, impurities or dislocations which can trap an electron or hole and hold it until a pair is completed. Such carrier traps are sometimes purposely added to reduce the time needed to reach the steady state. 14. Doping. The conductivity of semiconductors may easily be modified by introducing impurities into their crystal lattice. The process of adding controlled impurities to a semiconductor is known as doping. The amount of impurity, or dopant, added to an intrinsic, pure, semiconductor varies its level of conductivity. 15. Doped semiconductors are referred to as extrinsic. 16. By adding impurity to the pure semiconductors, the electrical conductivity may be varied by factors of thousands or millions. 17. A 1 cubic centimeter specimen of a metal or semiconductor has the order of 1022 atoms. 18. In a metal, every atom donates at least one free electron for conduction. Thus 1 cubic centimeter of metal contains on the order of 1022 free electrons. 19. Whereas a 1 cubic centimeter sample of pure germanium at 20 degrees Celsius contains about 4.2 1022 atoms, butanol 2.5 1013 free electrons and 2.5 1013 holes. The addition of 0.001% of arsenic, an impurity, donates an extra 1017 free electrons in the same volume, and the electrical conductivity is increased by a factor of 10,000. 20. 21. The materials chosen as suitable dopants depend on the atomic properties of both the dopant and the material to be doped. In general, dopants that produce the desired controlled changes are classified as either electron acceptors or donors. Semiconductors doped with donor impurities are called N-type, while those C-doped with acceptor impurities are known as P-type. The N and P-type designations indicate which charge carrier acts as the material's majority carrier. The opposite carrier is called the minority carrier, which exists due to thermal excitation at a much lower concentration compared to the majority carrier. 22. For example, the pure semiconductor silicon has 4 valence electrons that bond each silicon atom to its neighbors. 23. In silicon, the most common dopants are group 3 and group V elements. Group 3 elements Sal contain 3 valence electrons, causing them to function as acceptors when used to dope silicon. When an acceptor atom replaces a silicon atom in the crystal, a vacant state, an electron hole, is created, which can move around the lattice and function as a charge carrier. Group V elements have 5 valence electrons, which allows them to act as a donor. Substitution of these atoms for silicon creates an extra free electron. Therefore, a silicon crystal doped with boron creates a P-type semiconductor, whereas one doped with phosphorus results in an N-type material. 24. During manufacture, dopants can be diffused into the semiconductor body by contact with gaseous compounds of the desired element, or ion implantation can be used to accurately position the Doped regions. Amorphous semiconductors. Some materials, when rapidly cooled to a glassy amorphous state, have semiconducting properties. These include B, Psi, Ge, Se, and Te, and there are multiple theories to explain them. 25, 26. Early history of semiconductors. The history of the understanding of semiconductors begins with experiments on the electrical properties of materials. The properties of the time-temperature coefficient of resistance, rectification, and light sensitivity were observed starting in the early 19th century. Thomas Johann Seebeck was the first to notice an effect due to semiconductors, in 1821. 27. In 1833 Michael Faraday reported that the resistance of specimens of silver sulfide decreases when they are heated. This is contrary to the behavior of metallic substances such as copper. In 1839, Alexandre Edmond Becquerel reported observation of a voltage between a solid and a liquid electrolyte, when struck by light, the photovoltaic effect. In 1873, Willoughby Smith observed that selenium resistors exhibit decreasing resistance when light falls on them. In 1874, Carl Ferdinand Braun observed conduction and rectification in. Carl Ferdinand Braun developed the crystal detector, the first semiconductor device, in 1874. Metallic sulfides. Although this effect had been discovered much earlier by Peter Munkath Rosenskjold, SV, writing for the Annalen der Physik und Chemie in 1835, 28, and Arthur Schuster found that a copper oxide layer on wires has rectification properties that ceases when the wires are cleaned. William Grills Adams and Richard Evans Day observed the photovoltaic effect in selenium in 1876. 29. A unified explanation of these phenomena required a theory of solid-state physics, which developed greatly in the first half of the 20th century. In 1878 Edwin Herbert Hall demonstrated the deflection of flowing charge carriers by an applied magnetic field, the Hall effect. The discovery of the electron by J.J. Thomson in 1897 prompted theories of electron-based conduction in solids. Carl Baedeker, by observing a Hall effect with the reverse sign to date in metals, theorized that copper iodide had positive charge carriers. Johann Koenigsberger classified solid materials like metals, insulators, and variable conductors in 1914, although his student Joseph Weiss already introduced the term Halbleiter, a semiconductor in modern meaning, in his PhD thesis in 1910. 31. Felix Bloch published a theory of the movement of electrons through atomic lattices in 1928. In 1930, B. Gooden stated that conductivity in semiconductors was due to minor concentrations of impurities. By 1931, the band theory of conduction had been established by Allen Hayes Wilson and the concept of band gaps had been developed. Walter H. Schottky and Neville Francis Mark developed models of the potential barrier and of the characteristics of a metal semiconductor junction. By 1938, Boris Davidoff had developed a theory of the copper oxide rectifier, identifying the effect of the p-n junction and the importance of minority carriers and surface estates. 28. Agreement between theoretical predictions, based on developing quantum mechanics, and experimental results was sometimes poor. This was later explained by John Bardeen as due to the extreme structure-sensitive behavior of semiconductors, whose properties changed dramatically based on tiny amounts of impurities. 28. Commercially pure materials of the 1920s containing varying proportions of trace contaminants produced differing experimental results. This spurred the development of improved material refining techniques, culminating in modern semiconductor refineries producing materials with parts per trillion purity. Devices using semiconductors were at first constructed based on empirical knowledge before semiconductor theory provided a guide to the construction of more capable and reliable devices. Alexander Graham Bell used the light-sensitive property of selenium to transmit sound over a beam of light in 1880. A working solar cell, of low efficiency, was constructed by Charles Fritz in 1883, using a metal plate coated with